Prior to the advent of the .NET framework, most of us were accustomed to our Windows applications having free and unfettered access to all of the local resources on a PC, including the registry, file system, event logs, environment variables, or other resources. This startling and disturbing lack of security made for some interesting times for many users, developers, and of course, IT management. Due to the inherent limitations of role-based security, we developers and users were kind of conditioned to accept that nothing was really off limits for a running application as long as the user was authorized to use the resource. In many cases, the users, and by extension their applications, would have an inappropriate administrative level of access on all system resources. On occasion, this access would cause a significant level of angst and frustration for all concerned. With the proliferation of distributed component-centric systems, it's not uncommon to see applications download and execute components from the intranet or from network shares. The potential negative consequences for such applications are really pretty obvious. Malicious code, whether by design or not, could be loaded from an external entity and could wreak havoc on a local computer or network on which it resides. In this day and age, privacy and security are a paramount concern. The threat of security breaches that could jeopardize privacy or sensitive data is a constant issue. So, what was needed is an integrated security model that grants code permission to resources based on evidence pertaining to the credentials encapsulated within an assembly. The .NET framework provides that security model, and it's called Code Access Security. Code Access Security is a mechanism that helps limit the access to code, or more precisely, an application has to protected resources and operations. In the .NET framework, Code Access Security defines permissions and permission sets that represent the right to access various system resources. It enables administrators to configure security policy by associating sets of permissions with groups of code. It enables the code to request access that it needs in order to run. Code Access Security limits what an application is allowed to do. Suffice it to say that there's a great deal more to learn about Code Access Security, and all of that is beyond the scope of this course. I highly recommend that you spend some time with the .NET documentation and with MSDN in order to gain an effective understanding of the nuances of this very important topic. Now let's talk about garbage collection. Every program uses resources of one sort or another. It could be memory buffers or screen space, network connections, database resources, and so on. To use any of these resources requires that memory be allocated to represent the type. The Microsoft.NET Common Language Runtime requires that all resources be allocated from the managed heap. Now, objects are automatically freed when they're no longer needed by the application. So this, of course, raises the question: how does the managed heap know when an object is no longer in use by the application? Well, there's garbage collection, and there's a specific garbage collection algorithm, or GC algorithm, that is used by the Common Language Runtime. The way it works is actually pretty ingenious. When a process is initialized, the runtime reserves a contiguous region of address space that initially has no storage allocated to it. This address space region is called the managed heap. The managed heap maintains a pointer that indicates where the next object is to be located within the heap. So an application will create an object using the new operator, and this new operator first makes sure that the bytes required by the new object fit within the reserved region, and if it doesn't have enough storage there, it'll commit storage if it's necessary. If the object fits, then the pointer points to the new object in the heap, and this object's constructor is then called, and the new operator returns an address for the object. The garbage collector can free any unused objects, and it can reposition contents of the heap. So if you'll recall, this is the behavior that I described during our discussion about delegates. There's some pretty complex algorithms there that the GC uses in order to determine the life of any given object. The garbage collector checks to see if there are any objects in the heap that are no longer being used by the application, and if there are unused applications or objects that exist, then the memory used by those objects can be reclaimed. Now, if no more memory is available for the heap, then the new operator would throw an out of memory exception, and you'd be notified that you don't have enough memory to allocate a new object. You can also manually fire the GC, but let me tell you, that procedure is really not recommended. Needless to say, the managed environment and the GC are pretty sophisticated. Now, here's the good news about the GC. Its operation is completely transparent to you, the developer, and to your users. Over the course of this lesson, you've heard me refer to the Common Language Runtime a number of times. The Common Language Runtime is something that I'd like to nail down just a little bit more and make sure that we all have a real good understanding of what it is. So the Common Language Runtime, or CLR, is Microsoft's commercial implementation of the Common Language Infrastructure, or CLI, specification, and it's actually a very important part of the Microsoft .NET framework. At its most basic level, it's the infrastructure that executes applications and allows them to interact with other parts of the framework. It provides important capabilities in optimizing and securing and providing many robust capabilities such as application deployment and side-by-side execution, which we've talked about before. The code that you develop with a .NET language compiler that targets the CLR is called managed code, and again, we've talked about that before. It allows multiple language development and integration, and of course benefits from features such as cross-language exception handling, enhanced security, versioning, and deployment support, and a simplified model for component interaction, debugging, and profiling. Applications created outside the .NET environment that are not targeted to use the CLR are called unmanaged code. So there's the difference, managed code versus unmanaged code. But beyond all of that, you need to know that the Common Language Runtime, or the CLR, is the foundation upon which Microsoft and their .NET strategy is built. The CLR provides a robust execution environment that manages running code and provides all the services that make software development easier. Services available in the CLR include automatic memory management. We talked about that with the garbage collection, cross-language integration, interoperability, and a very simplified deployment. So again, it is a very, very robust environment. Well, we sure have covered a lot in this lesson. We've had an introduction to namespaces, and we've talked about .NET language topics and intermediate language and metadata assemblies, and we've talked about how the compilation of MSIL is and the just-in-time compilers. We've also touched on security and garbage collection, and of course throughout this whole process we've touched on from time to time the Common Language Runtime. So all in all, quite a information-filled block of instruction. So now it's time to move on to the core of all of this, Net COBOL for .NET, and that's the next lesson. See you there.